Hello and welcome to The Daily Space. I am your host, Dr. Pamela Gay.
And I am your host, Beth Johnson.
And we're here to put science in your brain. And it turns out a lot of science starts with stunning images, including images of wind triggered aurorae on Saturn that solve scientific big problems, a dwarf galaxy that is just pretty, and so much Mars news.
Plus, we'll be joined by our guest, Dr. Adam Szabo, the mission scientist for the Parker Solar Probe, as we take a look at this record setting spacecraft and its plans for the future.
Stay tuned. One of the really pleasing things about astronomy is how pretty the data can be. A lot of times, a research project will start out with a person or a team taking the newest, highest resolution, longest exposure image of something that is thought to be scientifically interesting. Almost immediately, you can tell this is gonna be gorgeous. And you spend a few days or weeks, depending on the complexity of your setup, getting the best possible version of that image put together. And then you spend months or years trying to understand what the heck the image means. But at least when you're asked, what you doing? You can say, look, this pretty picture, I took it. And right now, if you ask the researchers behind a new stunning image of the dwarf irregular galaxy NGC 1705 what they are doing, they will say, analyzing this pretty picture. Maybe not that way, but this system is 17 million light years away, which is roughly 7 times further than the Andromeda Galaxy. The system is rich in young hot stars that pierce their surroundings with ultraviolet light. This data picks up the red nebulosity of surrounding hydrogen gas glowing red under the ultraviolet light. According to the release that accompanied this image, astronomers aim to discover thousands of emission nebulae, regions created when hot young stars bathe the clouds of gas surrounding them in ultraviolet light, causing them to glow. Until the research comes out, we have this pretty picture to hold us over.
Sometimes it is all right to just look at the pretty pictures. So we are now going to look from pretty galaxies to a pretty new view of Saturn. The image that we're showing is built up from infrared data acquired by the Keck telescope in Hawaii, and it shows how Saturn's south pole can be ringed with strong aurorae. Using a month of data, they were able to map circulation patterns in Saturn's atmosphere that reveal the aurorae are driven by atmospheric winds and generate radio emission pulses that have made the measurement of Saturn's rotation rate harder than it should have been. The radio pulses actually make Saturn look like it rotates with a variable length day, but it doesn't. It just has variable winds that generate changing aurorae. This kind of aurora is very different from what we have on Earth, but actually matches early explanation for Earth's aurorae. According to study co author Tom Stallard, this search for a new type of aurora harks back to some of the earliest theories about Earth's aurora. We now know that aurorae on Earth are powered by interactions with the stream of charged particles driven from the sun. But I love that the name aurora borealis originates from the dawn of the northern wind. These observations have revealed that Saturn has a true aurora borealis, the first ever aurora driven by the winds in the atmosphere of a planet. This work appears in Geophysical Research Letters with first author Nahid Chowdhury. Not everything space related is composed of pretty pictures of objects in space, though. Sometimes we also have pretty images of things going into space. We now go to Eric Mattis for news on a recent launch and how Starlink is trying to do good with their tech.
On February 5th at 0700 UTC, a Soyuz 2.1A frigate launched the Cosmos 2553 satellite from the Posets Cosmodrome in northern Russia. Let's watch the launch. Cosmos 2553 is a classified satellite for the Russian Ministry of Defense, but still mentioned a little bit about its mission. People following the Russian space industry through public sources think this satellite is the first of a new type of radar satellite called Nitron. According to the Russians, it is equipped with, quote, newly developed onboard instruments and system for testing under the influences of radiation and heavy charged particles. End quote. This mission makes sense given what orbit it was tracked in. According to the US military, it was inserted into a circular 2,000-kilometer orbit inclined 67 degrees to the equator, which happens to be right into the lower Van Allen radiation belt. The Fregat upper stage was deorbited on its second orbit safely into the ocean. During our in-depth segment on the eruption of the Hunga Hunga Ha'apai volcano, we mentioned that Starlink is hammering the night sky for research astronomy, but it may be worth it if it's usable in an emergency such as the Tonga eruption. This now seems to have happened, according to an article in the Fiji Broadcasting Corporation News posted last week. SpaceX engineers are in the country setting up a ground station for Starlink, according to the Minister for Communications for Tonga. The ground station will be set up for 6 months until the current undersea fiber optic cable is repaired. This is a nice gesture, but with only one ground station, the total bandwidth available is limited. Still, as the Starlink constellation is currently set up so that satellites can only send signals when the customer and a ground station are both in sight, it's better than nothing. The inter-satellite links are not operational, and even then, the satellites with the links are a small fraction of the total constellation and in specific orbital planes. Now we move away from interesting pictures and Earth matters to look at water and Mars. Again. Stay tuned.
When we think of Mars, we think of a red planet, barren, covered in dust and rocks and ancient lava flows. There's an ongoing debate about the existence of liquid water under the polar ice caps. We've tracked seasonal changes with a host of satellites. And we have a small collection of rovers wandering the surface, sampling, analyzing, and collecting rocks. There are sedimentary rocks that were clearly created due to the flow of water. We've seen pictures of stream channels and river deltas. Perseverance landed in what we think was an ancient crater lake bed. And yet, no life. Granted, Percy is the first rover really tasked with looking for signs of life, and even it's not allowed to sample where we think life could still be if it were there. We seem, on the whole, to be hopeful that we'll find evidence of life or past life because of that wet history of Mars, even if most of the water is gone, whether it has escaped the thin atmosphere or gone underground. Now, in a new paper published in the Proceedings of the National Academy of Sciences, a NASA-funded simulation of past Mars has revealed that the red planet was wetter for longer than previously thought, about 500 million years longer. The research into Mars's past conditions is not an easy task, as co-author Michael Way explains. Discerning the climate of Mars approximately 3 billion years ago is challenging because the Martian surface features do not seem to fully support either a warm and wet or cold and dry climate during that time. A warm and wet climate would have produced extensive erosion from flowing water, but few valley networks have been observed from this age. A too cold climate would have kept any northern ocean frozen most of the time. A moderate cold climate would have transferred the water from the ocean to the land in the form of snow and ice, but this would prevent tsunami formation, for which there is some evidence. This new simulation found not only a cold and wet Mars was possible, but there might have even been a stable ocean in the northern hemisphere where the atmosphere was denser and warm. That would make it possible for the water to evaporate, but then fall back to the surface as rain or snow. In nearby highland regions, the snow could accumulate enough to become glaciers, and those glaciers would flow back down to rejoin the ocean. And that northern ocean means a mechanism for circulating warmer water to the North Pole, raising temperatures there as well. Factor in the evidence that Mars's atmosphere was thicker in the past, and you can now keep Mars warm for a longer period of time than previously thought. A warmer, wetter planet for an extra 500 million years gives you that much more time and the right conditions for life to develop. The evidence is piling up for a habitable past Mars, and I'm excited to contemplate what future rock samples might find.
Of course, knowing that Mars had water isn't a new thing. As mentioned in the previous story, we've seen evidence of riverbeds, stream flows, and lakes. The water was there, and now it's not. That's definitely not a question. The question is what made the water disappear? It turns out that early in Mars history, when there was a northern ocean and precipitation and wetter conditions, there was also a magnetic field similar to what we have here on Earth. That magnetic field helped protect Mars' atmosphere, which kept the water on the surface. Then the magnetic field disappeared, and in new research published in Nature Communications, a team has possibly solved just why that magnetic field went away. Co-author Kaya Hirose explains the logic behind these recent simulations. Earth's magnetic field is driven by inconceivably huge convection currents of molten metals in its core. Magnetic fields on other planets are thought to work the same way, though the internal composition of Mars is not yet known. Evidence from meteorites suggests it is molten iron enriched with sulfur. Furthermore, seismic readings from NASA's InSight probe on the surface tell us Mars' core is larger and less dense than previously thought. These things imply that the presence of additional lighter elements such as hydrogen. With this detail, we prepare iron alloys that we expect constitute the core and subject them to experiments. And once again, we see scientists getting to play with diamonds and lasers. They placed a sample of material containing iron, sulfur, and hydrogen. These are the elements they think Mars' core used to be made from. They then placed the sample between two diamonds, compressed it, and hit it with an infrared laser. Observations were taken with X-ray and electron beams, and the team was able to see what happened as the sample melted under pressure and how the composition changed over time. Basically, the material separated into two liquids, which would have given Mars the convection currents necessary to make a magnetic field. Eventually, however, the two liquids completely separated. The currents went away, and with those, the magnetic field disappeared. Without the magnetic field, the atmosphere got blown out to space by the solar winds, and the water vapor in the air broke down and escaped, followed by the time surface water as it evaporated over time. So life could have developed, but it likely only had a narrow window to do so, even if that window is slightly longer than we originally thought. Speaking of solar wind, we'll be joined in a few moments by Dr. Adam Szabo to talk about the Parker Solar Probe and what we are learning about the solar wind. Stay tuned.
The Parker Solar Probe continues to wow scientists and the public alike with its record-breaking speeds and approaches to the sun. And now it's set to reach perihelion again this month on February 25th. The main mission objectives for the spacecraft are to, quote, unlock the mysteries, unquote, of the sun's corona, and it will do so by tracing how the flow of energy heats and accelerates the solar corona and the solar wind, determining the structure of the magnetic fields that create the solar wind, and exploring how all those energetic particles get sped up and transported. And this has to be a very hardy spacecraft to perform all that science. The Parker Solar Probe will eventually get within 9 solar radii of what we consider to be the surface of the sun. That's only about 3 million kilometers away. At that point in time, the probe will be moving at almost 700,000 kilometers per hour, and the temperature of the solar shield on the craft will reach about 1400 degrees Celsius. It's an amazing mission, and although this upcoming perihelion is the 11th pass so far, there are still at least 3 more years of data to collect, including 2 more flybys of Venus and another 13 close approaches. We're always excited to see what new information is gleaned from Parker about the sun. Joining us now is Dr. Adam Szabo from NASA Goddard Space Flight Center. Dr. Szabo is the mission scientist for the Parker Solar Probe, and his research specializes in heliospheric and magnetospheric structures, including shocks and discontinuities. Thank you for joining us, Dr. Szabo, and welcome.
Thank you very much for the invitation.
Oh, you're muted. Oh, there you go. Nope, we got it. We hear you now.
Yeah, thank you very much for the invitation.
Oh,
Can
thank you
you
for
hear me?
joining us. So tell us about the Parker Solar Probe. What's this mission about? What are we trying to do with this particular spacecraft?
Parker Solar Probe is a flagship mission for NASA's Heliophysics division. Its primary objective is to understand where does the solar wind that the Earth is immersed in coming from. The solar wind is the expanding upper atmosphere of the sun that encompasses the whole heliosphere, the space that all the planets live in, including Earth. We know about the solar wind for a really long time, since the beginning of space age, but it remains to be a big question. How do these particles get accelerated and swept out from the vicinity of the sun? That's one of the main objectives of Parker Solar Probe, to understand by going closer to the sun than any mission before. It is one of these questions that we try to study it from large distances away from the sun. It's very, very difficult to collect sufficient amount of information to really resolve the many competing theories. So it really comes down to that we just have to go there where the acceleration happens. Another aspect that we are after, unless you
Go
want
ahead.
to, another aspect is that the sun is also the source of solar energetic particles. These are particles astronauts worry about, satellites worry about. So both people and technology. Solar energetic particles are accelerated again near the sun. And in order to really understand sufficiently the physics of this acceleration, we need to be there. And there, the purpose would be not just a basic understanding, but enough understanding that we can develop predictive capabilities.
So why are astronauts and satellites concerned about the solar wind? Will you explain that?
So the solar wind is sort of the backdrop over which everything happens in the heliosphere. So the solar wind itself is not terribly dangerous for astronauts or spacecraft in general, but we need to understand it in order to get an idea how do the more destructive or dangerous structures propagate in it. So, for example, many people heard about corona mass ejections, abbreviated as CMEs. These pose significant threat not just to spacefaring people and satellites, but all the way down here on Earth, as these big structures impinge on the Earth's magnetosphere. In order to be able to predict the travel, the propagation, and arrival of these CMEs, we need to understand the background in which they propagate.
So how does the Parker Solar Probe study this? It's getting very, very close. I understand that several records are being set. How close are we talking?
So Parker Solar Probe, the team took an incremental approach rather than trying to get as close as possible on the first shot. And we decided that we were going to do this in a stepwise manner, where each orbit, well, every several orbits, we do a Venus encounter, which allows us to lower our perihelion or closest point of approach to the sun and get just a bit closer, review the data, how are we doing, and then get a little bit closer, thus maximizing the science return and minimizing the risks. We just started our 11th encounter with the sun. We are going down this time around. The closest approach will be at 13.3 solar radii. We use the sun's radius as a measure because it's sort of easier to imagine. If you see a picture of the sun, you can see what is the radius or half the diameter. And so we are 13.3 times that radius at the point of closest approach. That's not the closest we will get. We will go below 10. That's the closest we can get, given today's technology. But 13 is really, really close. We passed a long time ago the previous record holder. That was a European mission called Helios. That was sort of around 30 solar radii. So we are well, well below, and we are seeing conditions never seen before.
So, what are some of the things that you're seeing now?
So the first time we crossed over what is called the Alpine radius around the sun. This is a point below which the solar wind is not so supersonic any longer. So let me start just a little bit of background here to understand the importance of the crossing of this boundary. The solar wind, when it starts its life from the surface of the sun, obviously doesn't start immediately going at really high speeds. It starts at a lower speed and it picks up speed as it travels away from the sun. One of the things that we do not understand, that rather than just sort of leaving like a boiling pot of water, that you have water molecules coming out, it's sort of shut out and then it's sort of going at a constant rate of speed. When the solar wind particles travel through the upper corona, which is the outer atmosphere of the sun, one can see during solar eclipses. When the solar wind travels through that region, all of a sudden it really speeds up. I mean, several times over increases its speed, and it becomes supersonic, in a sense like a supersonic airplane is going faster than the speed of sound. The solar wind starts to travel faster than any of the electromagnetic waves that can travel inside the plasma medium of the solar wind. Uh, that's one of our objectives, to understand exactly how does the solar wind do that. It clearly does it, so it's physically possible. We have competing theories that tries to explain exactly what happens. In order to distinguish between these theories, we need to have data to tell who is right, who is wrong, or possibly nobody is right, and we need to go back to the drawing boards and come up with a new one, a new theory. So the critical thing is that below the off-in point, the solar wind is still subsonic, going slower than the local electromagnetic waves. That means that information can propagate back and forth to the surface of the sun. When the solar wind is faster than when it's supersonic, when it's faster than the electromagnetic waves, that means that whatever happens in the solar wind, even if a wave tries to propagate backwards, the medium is moving faster than the wave. So that wave will never make it back to the sun. Informationally, communication-wise, there is lack of communication between the sun and the solar wind. Below the off-in point, there is two-way communication back to the surface. Now, many people think some of the theories argue that this is the environment one needs in order to accelerate the sun, because counter-propagating waves can they can add together and dump energy into the solar wind, speeding up. But so this type of solar wind we have never seen before. So this is one of the new discoveries. We are still scratching our head. So I am anticipating that you will ask me that. So how does this new kind of solar wind look like? And and all I can tell you at this point that it is slower. I can tell you that the wave modes that we see them look different, but literally we just got it on the ground, this kind of data, and said, we've been waiting for this moment that when we can see that it's slow enough, that it is subsonic, and we are still sort of putting it all together. That okay, so what did we learn from it other than it's different?
Well, that is very exciting. This mission is one of those ones we keep watching, because not only for the science, but also just for some of those record-breaking aspects of it, like how fast it's going, how close it's getting. And I'm looking forward to this next close approach, which is coming up in just a couple weeks, I think.
Yes, February 25.
Wonderful. So thank you, Dr. Szabo, for joining us here today. It has been fabulous having you. So thank you for coming.
Thank you so much. Bye.
This has been The Daily Space. To all of you watching, this conversation ran longer than we can air here on Now Media. You can catch the interview in its entirety on our website, dailyspace.org.
While you're there, check out our show notes to find out more information on all the stories, including images. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.